I'm really delighted that we have not one, not two, but three luminaries here to talk about this on the panel. So Brian, Klaus, and Aki will help us interpret some of the questions, and then we really encourage you to ask anything that you would like to at the end as well. So I'm going to start with Klaus, and I'm going to give him a chance to tell us a little bit about his business, and first just say thank you for joining and jumping right in on the panel to participate and contribute. So I think it'd be good for this audience to know, what are the technology trends that are really affecting your business in mask repair?
So let me first thank you for inviting me to this panel. It was really a pleasure to be here. And about the technology trends of the last years, that was clearly the extension of 193 lithography that put a lot of stress on the repair, especially because there are quite a large number of new mask types that came out with different materials. And since we are a chemistry-based repair process, that means we had to develop repair recipes for those different mask types, and this is still continuing till today. At the same time, because of the extension, there is a tighter specs on the performance of the repair, and that has within an accelerated timeline. So basically, we speed up on the development to meet the demands of the industry.
Okay, let me follow on because there was an article just last week in Semiconductor Engineering, a good article covering what's ready and maybe what's not for 10 nanometer on masks, and they raised a question in the article: was mask repair ready? So what do you have to say about that? Not putting you on the spot, but
sure. So I certainly believe that mask repair is ready for the 10 nanometer and beyond. And I mean, as I said, we learned from that challenge that we had. So with the eBeam based process, there are two areas where we needed to improve. One is find new chemistry, and by now we better understand the chemical processes, and we have added new chemistries to tackle these new mask materials. At the same time, having tighter specs means, in the past it was quite easy because the eBeam has a very small spot size, and so meeting minimum feature size was not really an issue at all. That changed over the last, I would say, 2 years, where we reached the limits of what the 1 kV beam, that's what we are using for the repair, can do. And the answer to that is that we lowered the electron beam energy, because the performance is governed not by the primary beam size, but by the scattering within the substrate that then leads to the chemical reaction. And by lowering the beam energy, that spread gets smaller, and therefore the process resolution improves. And so basically, we are now able to address all mask types that are on the market and for the foreseeable future, and also have a clear path into the future in terms of even lowering the beam energy more to keep pace with smaller feature sizes.
Okay, pretty clear answer then. Yes, that's right.
So could I make a comment
Yes.
on repair? Unfortunately, the repair business isn't like a kimono. One size doesn't fit all. If you really look at the repair, if you look at what goes on in the mask shop today, they don't only use one technique. And if you look at the techniques today, there's focused ion beam, there's eBeam repair, there's nano machining, and there's a laser. And if you look at any mask shop today, they use more than one technique. And I believe that there will be multiple techniques in repairing masks, because there are different chemistry works. I'm a chemist, I know chemistry works, but sometimes you have to use other techniques. So it's going to be not only a function of the type of substrate, but it's also going to be a function of where the defect is, and also what the size of the defect or the type of defect. So I believe that there are many options that will continue to be used in the mask shops.
Okay, well, we're going to stick with you, Brian, because
Okay.
I think for those who do know Brian, he's got at least one opinion on the topic of EUV. So I'm going to ask him, what's your take on all of the optimism that showed up in this year's survey, and what's left to be done? What are still the technical challenges?
Well, first of all, I'd call the optimism more the marketing effect than technology, but there's no question that there's been tremendous progress made in EUV. I mean, you can't deny that. But the concern I have is if I go to all of these conferences, which I attend a lot of them, I don't see a lot of mask data. You see, the one chart that you always see at every conference is how many defects they've reduced in the blank. You don't really see anything about what the costs are. You don't see what the overlay performance is. You don't see how stable the multi-layer is going to be over long-term use. The real issue is, masks are like automobiles. They all look good in the showroom. You don't really know how well it's going to perform until you get out and drive it. And that's really what the situation is going to be when you get into high volume manufacturing on any mask technology. And I've been in the mask business for almost 40 years. Every technology node would always present you with a new mask defect or a new mask anomaly that you had to deal with. So it's easy to sit by and theoretically figure out what the issues are going to be, but you're not really going to know what the mask issues are until you really start hitting them with 500 volts or 1 kV. I guess that's the new target, right? So the mask data is based on very, very low dose, very low energy exposures. We'll wait till you get to high volume manufacturing, and then you'll really see what the issues are.
Okay.
And I think the other challenges with respect to EUV are very well documented, source and reliability and whatnot. But I'm concerned about the mask issues.
Yep. Very appropriate comments for this group. So Aki, let's get you involved here. But first, again, I think we just really want to say thank you for your leadership and commitment to the eBeam initiative. And without it, I don't think we'd be in this room today. So I just want to hear from you about what you found as interesting or surprising out of the perception survey.
From the perception survey, let's see, I think the EUV complexity question was an interesting one for me. It was more about everybody realizing that EUV masks are going to be complex, because I think the easy thing to think is there isn't going to be as much OPC, it's not going to be IoT on EUV, so the shapes are going to be less complex. But it turns out there's a lot of other effects that you have to correct for. So at the end of the day, you may end up with EUV masks that are very, very complex. I think you saw on the survey results, this is a perception survey, right? Right? But the perception is that there may even be curvilinear shapes on the masks. I wouldn't have said that, but that people think that 75% maybe, total thought that the masks are going to be complex shapes. Not just the shape count is going to be high, which is certainly true, but the shapes are going to be themselves complex. That surprised me.
Well, let's go back now to multi-beam for a few minutes. And why do you think the mask makers are so optimistic about multi-beam? Do they know something?
It's an interesting thing, right? I mean, most of the businesses around the world, you would have the vendors pushing through marketing programs to the customers saying, it's ready now, you should buy it now, right? And the customers are going, are you sure it's really ready? I mean, we have a reverse, both in EUV and multi-beam. We have a reverse, right? The customers are saying, we need it now. It's ready, give it to us. And the vendors, or not necessarily the vendors themselves, but the community of equipment makers are going, I don't know, these things are harder than you would think, right? There's always going to be a surprise at the end. So, this really speaks to the power of Moore's law not work. It's really hard to keep up, and it's the costs exploding, and everybody needs a lot of help, and they need the help faster than probably the suppliers are able to supply, right? So it's a great place to be in terms of demand is higher than supply. So you would think the prices are going to go up, but we all have problems. So I'm not sure how that's working. But anyway, I thought that's interesting. It's I think it's also noteworthy that even though as you saw, the multi-beam progress is incredible, and I hope that it's going to come in 2016. I hope it's going to come in 2017 or 18 or whatever the survey said about when it's going to be in high volume production. But even after it starts to be adopted, it's going to take a while before all of the VSP machines are out, right? So being able to write these complex mask shapes, particularly for ARF, there's no question in ARF masks it's going to be there. So, and even on EUV, there's going to be complex masks. I think being able to write those on conventional VSP machines is going to continue to be important.
Thank you.
Could I make a comment about why the mask makers are more
Yes,
optimistic?
please.
The reason they're more optimistic is the mask makers have been using eBeam lithography for 30 years, and so they really understand the issues. And the science is well known. I mean, if you really look at the challenges of getting multi-beam into manufacturing, they're really engineering challenges, they're not science. The science is well understood. If you go to the literature and do a search on eBeam proximity correction, you'll find that there are over 37,000 papers published on how to deal with eBeam proximity effects. So the science is out there, the science is well defined. It's been around since Bell Labs developed the eBeam system back in the late 60s, right? So I think, and mask makers have been using, I brought in the first eBeam mask maker in IBM in 1976. So mask makers have been using eBeam technology for years. So I think that's where the optimism comes from.
Okay.
Are you contrasting that to EUV?
I won't comment.
Well, actually,
comment on that.
I think that is a good question. Both, there's so much positive, enthusiasm and confidence in both. But how these are two very different major developments. How are they different? How are they similar? Is there?
Well, my only comment is I believe before you do the engineering, you have to understand the science. And in some cases, when we go to advanced lithographies, we always seem to have the time to go back and understand the science when we run into roadblocks in engineering. And I'm always a firm believer, you have to understand the science before you do the engineering. That's the comment.
Yeah. Any other comments about that? How they're similar or different?
Well, I think they're both very similar in the demand being incredibly high. There's economic basis for it, and as well as technical basis for it in going down in size. So, it's a big industry driving a lot of money driving the need, and it's interesting to me. There was a comment this morning by somebody that said, if it helps to have bigger masks, why don't you just have them, fund the mask shops to do it? The amount of money required is much less than what you're funding, having to fund all of ASML or something. I think there are, some political structures involved, and then there are other technical things, and if there is an alternative, the alternative is to bet on something, on the lithography side, right?
So Klaus, I'm going to turn to you for the last sort of question, then we'll open up to anybody in the audience. We have one more question we want to get to, and that is, on all of the mass defect and repair rate success, any particular insights there? Any explanations for sort of this wide range on the repair rate success?
Well, I mean, first time success rate is about, in average, is 89%, which is quite good. On the other hand, there were a wide range going down all the way to 60%, and that's kind of surprising. And I would think that has to do with a particular mask type that is hard to repair, and it would be good to find out what that is. And on the other hand, the first time success rate is not everything, right? So what we with the eBeam technology, you can basically do a second repair because you can also add material then again if you overshoot, which is not the best thing to do. So what we integrated in our new design is an AFM, and the idea there is if you have a very difficult repair, you would just go to the AFM and look at the progress of the repair and then do some repair some more, so that would increase the second repair yield, and maybe that would also help for that low value of 60%. But again, I would need to know what actually the reason for that would be.
Okay, fair enough.